right, in this example, we have a 16 by 20 inch piece of cardboard, and we're going to cut squares from the corners and then fold up the sides to form an open top box. And we want to figure out, okay, so what size squares do we want to cut out of the corners in order to get a box with the maximum volume, right? So our objective is to maximize the volume of this box. And now, first thing we want to do is probably draw a picture. Now, there wasn't a picture drawn, so you'll have to draw one. I took the time to, I just put together a drawing here so you don't have to watch me try to draw something. And so, whoops. And so now I'm going to use this drawing here. Okay. Now, we want to assign some variables, right? Because we're going to write an equation for the volume of this box. And these squares, these corners are going to be squares. So what I'm going to call, I'm going to say that these are squares that are x by x, right? They're all going to be the same size, right? They're all going to be x by x. They're just going to be squares. And so I'm going to call the side lengths of these squares that we're going to cut out x. So, all right, so now we need a formula for the volume of the box, right? So when I fold up these sides, you know, the bottom of the box is going to be this dashed line, and then the height of the box is going to be x, right? So let's figure out what the dimensions of the base of the box are going to be, right? So originally this piece of cardboard was 16 inches wide, and we took out squares of length x on either side. So we're going to get 16 minus 2x will be the width of the box, okay, once we cut those squares out and fold it up. And then on the other side, now the length was originally 20, and we cut out 2 lengths of x. So this will be let's write 20 minus 2x, right? That'll be the length of the box. And then the height of the box will just be x once we fold up the sides. Okay? So here's our objective. Our objective is to maximize, we want to maximize the volume. Maximize the volume, right? We'll call it v. We'll call the function v, and we're just going to take length times width times height. All right, so we're going to have 20 minus 2x is the length. The width of the box is 16 minus 2x, and the height of the box is just x. All right. So there's our objective function. Now we don't have to worry about a constraint equation here, I guess, because you know, it's all in terms of one variable now. So, but this is our objective, and so once we have the formula written, then it's just the same type of problem we've been doing for the last few days, right? We've just been finding the maximum and minimum of functions, and so this is our function. Now, it'll probably be easier if I FOIL this out and expand everything, right? So I'm going to get 320. I'm also going to go and multiply through by the x. So 320x, and then the middle term, I'm going to have 16 times 2, and I'm going to, a negative, right? It's going to be a negative 32 and a negative 40. So that gives me a negative 72x, but then I'm going to multiply it through by this extra x over here. So I get 72x squared. And then the last term will be negative 2x times negative 2x, which is a negative 4x, 4x squared, and then we're going to multiply by the x. So we get plus 4x cubed. Okay, so that's what happens when I FOIL it out and then distribute that x. Okay, so now let's find the derivative, right? So we're going to find v prime of x b prime is just going to be, just take the derivative of this. We have 320 minus, okay, we bring down the 2, so it's 144x. And then, okay, then we take the derivative of the last term, we're going to get 12x squared. Okay, well, let's see. Now we had to set that equal to 0 in order to find the critical points, but I either need to factor this or I need to maybe use the quadratic formula. I think it would be easier either way if I factor out the greatest common factor. Just make smaller numbers, right? So I'm gonna actually factor out a this is 4 times 8 is 32, so it looks like the biggest thing I can factor out is maybe a 4. And I'm going to write these terms in reverse order, so I have the x squared term first. So that's going to be 3x squared, and then factor out, and I get minus 36x, and then plus 80. All right, now trying to set that equal to 0. All right, that's going to be tough. I don't know. Factors of 240 that add to a negative 36. Ugh, I don't know. I think what I need to do is just use the quadratic formula, because I don't know. That looks like it's hard to factor, and I might as well just use the quadratic formula. That'll give me the answer. All right, so x equals negative b, right? Negative b plus or minus the square root of, right? B squared, so we have 36 squared minus 4 times A times C, right? So notice I'm just ignoring the 4 out in the front, because if I find the roots of the quadratic in parentheses, that'll give me what I want. And then I need to divide this by 2a, which is 6. All right, so I'm just going to put this into my calculator and see what I get. So when I put this into my calculator, I get 2 answers. I get 9.055 and I get 2.945. Okay, so those are my 2 answers. Those are my side lengths. Now let's think about this because remember, this x represents the length of the squares, the side length of the squares that I'm cutting out. If I cut a 9-inch square out of the corners, there's going to be nothing left, right? There's nothing left. It's only 16 inches wide, so I can't cut anything more than 8 inches out of the corners. And even then, if 8 inches there'd be no box, right? It would have no width to it. So, so I can't cut 9-inch squares out of my corners. So I'm going to cross that one out because it doesn't make any sense. So this is the only possible critical point, right? This is my critical point right here. Critical point. That's my critical point. So given the context of the problem, the other answer doesn't make any sense because I wouldn't have a box left. Everything would be cut away. All right, so now that I have my critical points, I just need to test them. My critical point, my one critical point. And again, I think when you have a polynomial, the second derivative test is easy because it's easy to take the second derivative. So if I find the second derivative, I'm just going to get minus 144. Right, I'm just going back up to the original polynomial for the derivative, plus 24x. All right. And then I can evaluate the second derivative at 2.945, right? And when I do that, I put that into my calculator, I get a negative 73.32, right? That's less than 0, so it's concave down. Okay, concave down, looks like that. So I have a local maximum. Local max at x equals 2.945. All right. So I found the side length of the square that I want to cut out. Now, I have to go back and make sure I answer the question that was asked. It says, there's several questions, right? It says, in order to create a box with maximum volume, what size squares should be cut from the corners? Okay, we got that. That's the length x. And what is the maximum volume? Okay, so we need to find the maximum volume. If we cut this size square out of the corners, so let's look at the volume at 2.945, right? And that this should be the maximum volume. So I'm just going to go back up to the original equation for the volume, right? And now I could also look at the endpoints, right? I could evaluate, because I can't cut more than 8 inches from the corners, otherwise I don't have a box left. And if I don't cut anything out, there's nothing to fold up. So, my endpoints are essentially x has to be between 0 and 8, right? Realistically. And so I could also evaluate the endpoints. But if I look at v at 0, I have nothing, right? Because I don't have anything to fold up, so my volume would be 0. And also at 8, right? At 8, you're basically cutting away the, 8 plus 8 is 16, right? So it'd be cutting away the whole thing, so the volume would be 0. So the maximum has to occur at this point. And so if I plug that into my original equation, right? If I just put x, go back up here into 20 minus 2 times 2.945, and then take 16 minus 2 times 2.945, and then take that whole thing times 2.945. Gets a little ugly to write it all out, but I just want to make sure, I'm going back to the original equation for volume. I got that the volume is 420.11. Okay. Now the units, remember that if you go back to the beginning, that everything's in inches, right? All the dimensions are in inches, so this has to be in cubic inches, right? Because volume is measured in cubic inches, right? Inches by inches by inches. So all right, so what's my conclusion here? I think I have enough room if I scroll down, maybe to put the. Oops, it's not scrolling here. So what's my final conclusion? My final conclusion is that the maximum volume is 420.11 cubic inches when the squares, okay, when it's like when the squares cut from the corners are let's see here. Let me make. There we go. Now I can scroll a little bit. Okay, are 2.945 inches by 2.945 inches. Okay, so we're going to cut almost 3-inch squares from the corners in order to get the maximum volume. All right, that's it for this example, and I'll meet you in the next video for the last example, my favorite example. So I'll meet you there. Bye.